my this. No, sir. No.
Thank you very much for that nice introduction, and thank you for inviting me for this lecture. It's an honor and a privilege for me to deliver the 2018 TIFR JRD Tata Public Lecture. Since it was mentioned that TCS is a competitor for Infosys, let me give you something that happened at Infosys. So we moved to our new campus in Electronic City way back around 94, 95, and probably around 2000, we built a new corporate block for the top leadership to sit. We have a management council conference room where all the top leadership meet almost a weekly or a monthly basis, state-of-the-art room, etc. And we decided to name that room after JRD Tata. And Mr. Ratan Tata graciously came and inaugurated that room for us. So in the industry, we actually have respect for each other, work very closely. In fact, I would say, if you look at the success of the IT industry, it's because of our ability to compete and collaborate that has made what the IT industry is today. We respect each other, so the competition is fierce but fair, and I think that's what is needed to build a global industry. So I said, it's an honor and privilege because this lecture is named after TIFR, India's preeminent science research institute, and JRD Tata, who was an iconic Indian industrialist and philanthropist. JRD Tata is an inspiration to all Indians. Sandeep talked about his deep involvement with TIFR. He was instrumental in encouraging Professor Homi Bhabha, I believe, to start TIFR. JRD Tata was at the forefront of India's mission mode programs in science and technology. He was a member of the Atomic Energy Commission for 26 years from its inception. JRD Tata is credited with inclusion of nuclear science as a research area in Atomic Energy Commission. He was also instrumental in its translation into applications that benefited Indian citizens. So the Tata Memorial Hospital is a pioneer in using nuclear medicine in Asia and one of the leading centers in the world treating cancer. JRD Tata became the president of the Court of the Indian Institute of Science in 1955 and was president for 38 years. This laid the foundation for IISc, becoming a globally ranked university of repute today. JRD Tata continued the tradition of Jamsetji Tata in an important era where a newly independent India was on a path of modernization by leveraging the power of science and technology. So that's why it's an honor and a privilege for me to get an invitation to come and talk to you today. So in this lecture, I will share my thoughts on science, technology, and knowledge, because I believe, ultimately, science and technology will have to be converted to knowledge for the benefit of society, and that's why, I term this title as Science, Technology, and Knowledge. Now, we have come a long way since our species, the Homo sapiens, first made an appearance almost 200,000 years ago. The first discoveries and inventions that we associate with our species actually predates that. Evidence points to the fact that the stone tools were first introduced by Australopithecus africanus, kind of tongue twister, about 3.4 million years ago. And fire was first controlled by Homo erectus about 600,000 years ago. So our journey in science discovery, etc., started way, way, way back from actually the beginning. The most interesting phase of the history of our species is arguably the last 500 years that coincides with the start of the modern scientific revolution in the mid-16th century. I believe the watershed was the publication of Nicholas Copernicus on the revolutions of the heavenly spheres, a seminal work on the heliocentric theory in 1543. Ever since the advent of the modern scientific revolution, we have seen a fundamental transformation in scientific ideas across mathematical, physical, and biological sciences. The scientific revolution has powered the rapid societal and economic progress and the growth of institutions like universities that continue to be the centers of scientific research and education. While the basic framework of scientific inquiry, discoveries, and inventions laid out during the modern scientific revolution still applies, science and technology disciplines have evolved and adapted over the years. I will discuss the trends in science, technology, and the resultant knowledge that are emerging today. In 2016, the paper on gravitational waves, observation of gravitational waves from a binary black hole merger by scientists associated with the LIGO project was announced, and that announced the detection of gravitational waves was published. Apart from the stellar scientific impact, the involvement of over 1,000 scientists from over 90 institutions from many countries, including India, captured public imagination. While LIGO is an extreme case of big science that had $1 billion budget, the trend of increased international collaboration in science is asecular. According to one recent study, the number of multiple author scientific research publications with collaborators from more than one country more than doubled from 1990 to 2015, from 10% to 20%. So increased international collaboration. Not only is research becoming global, it's also becoming multidisciplinary. A report in Nature mentions that the percentage of research papers in science and engineering with reference to other disciplines increased from about 20% in 1980 to about 35% in 2010. Interestingly, a 2015 study by Elsevier notes that authors from India are among the most prolific in publishing interdisciplinary papers. Even when you look at a young domain of science like neuroscience, you will see this effect here. Neuroscience is a science that combines, of course, psychology, anatomy, molecular biology, development biology, cytology, mathematical modeling, computer science, electrical and other engineering sciences, and psychology to understand the fundamental and emergent properties of neurons and neural circuits. So by definition, neuroscience is multidisciplinary. Modern multidisciplinary neuroscience traces its origin to the neuroscience research program, weaving biology, chemistry, physics, and mathematics, started within the biology department at the Massachusetts Institute of Technology in the 1950s. So fast forward, the leading information technology of today is AI, that is artificial intelligence, and ML, which is machine learning. And this was inspired by the research of neuroscientists done about 3 decades ago. So it is interesting to note that AI and ML have come a full circle today and are the tools that neuroscience scientists use to analyze brain imaging data more efficiently. AI and ML are helping speed up the analysis in many other scientific disciplines as well. So LIGO is another example where detection of new classes of gravitational wave sources are enabled using AI and machine learning. So AI and ML are new tools that we have. These are technologies that made rapid advances recently, though introduced many years back, but they have now found application in many other disciplines. Ever since the advent of steam engine in 1765, we have witnessed a continuous stream of technology inventions that have improved human productivity. According to a report by Barclays analysts, if human productivity was 100 units in 1765, it is now increased to 3,000 units today. In fact, the last 5 decades has seen an increase in human productivity from about 1,500 units to 3,000 units. And this steep increase coincides with the adoption of IT, including personal computing, software, internet, email, mobile communication, etc. I believe that AI and ML follow in that impactful list. Now, why AI and ML are likely to impact our lives in fundamental ways in the near future, these are not without biases. Till recently, the general reason for bias was thought to be the fact that the IT research and industry community are predominantly male and socio-culturally homogeneous. However, a recent study from Stanford reveals something more fundamental. ML algorithms may be learning from society's deep-rooted biases. This study used word embedding to measure changes in gender and ethnic stereotypes over the past century in the United States. Word embedding is a class of algorithms that convert a word into a vector and maps it in a multi-dimensional space. Vectors closer together represent words that are closely associated with each other. For example, vectors for mainframe and computer would be nearer to one another compared to vectors for mainframe and microwave. The study found that adjectives such as intelligent, logical, and thoughtful were associated more with men in the first half of the 20th century. Since 1960s, the same words have increasingly been associated with women in every subsequent decade. Interestingly, in 1910, the adjective commonly used for women were charming, placid, delicate, etc. By 1950, the list included new adjectives such as soft, childish, colorless, etc. And by 1990, older adjectives gave way to newer adjectives like maternal, caring, protective, etc. So you can see, the biases that are there. So this reveals an immediate need to focus on important social aspects of emerging technologies like AI and ML. Why it is important to be more diverse while selecting AI and ML professionals, we also need to work on methods that try to caution us about the inherent biases in the data used to train AI and ML systems. One solution may be to explore assigning weights to the different data sources used to train AI and ML systems. This may need to be more sophisticated than older the data, lesser the weight, and include data from multiple sources from multiple countries. And this is again why I believe research has to be global and India must participate. Apart from inherent biases, we also need to carefully look at use cases where emerging technologies like AI and ML are being used. I'm just using AI and ML because I'm familiar with problems in computer science. I'm sure most of us have watched the 2002 Hollywood blockbuster Minority Report, which depicted a future in 2054 where pre-crime, a specialized police department apprehends criminals based on foreknowledge provided by 3 psychics called precogs. Well, this context is closer to reality. AI and ML are assisting humans in judicial decision making. Last year, a man in Wisconsin, USA, was sentenced to a 6-year prison term based on a report generated by a private proprietary software whose ML algorithm was unavailable for inspection. ML algorithms are increasingly becoming integral to human life and impacting our daily lives. They're making decisions by analyzing and interpreting the analysis of the prolific amounts of data that we and our gadgets are generating. From the mundane, like what route we need to take to reach our destination, to more serious life-saving contexts of helping doctors choose an appropriate cancer therapy. It's imperative that the ML algorithms we design are robust. In spite of these challenges, I remain hopeful that we will overcome them. As with many technologies in the past, there was always a threat new technologies pose to humans. We have been resilient and ensured that these technologies, by and large, were ultimately used for the greater benefit of humanity. So one useful reference to examine the beneficial impact of new development in science and technology is to study the continuum of industrial revolution. The first industrial revolution took place in the 18th to 19th century in Europe and America. It was a period when mostly agrarian and rural societies became industrial and urban. The iron and textile industries, along with the development of steam engine, played central roles in the first industrial revolution. The second industrial revolution took place between 1870 and 1914. It was a period of growth for iron and textile industries and expansion of new ones such as oil and electricity. This era witnessed the use of electric power to create mass production. The major technological advances in this era include telephone, light bulbs, phonograph, and internal combustion engine. The third industrial revolution refers to the advancement of technology from analog, electric, and mechanical devices to the digital technology available today. The era started during the late 60s, early 70s, and is still ongoing. Advancements during this era include personal computer, internet, mobile phone. Now we are at the beginning of the fourth industrial revolution. It's an emerging era powered by the current advances in science and technology. It's characterized by the fusion of technologies that blurring the lines between physical, digital, and biological domains. So a question that comes to our mind is, what is the use of scientific discoveries, technological inventions, and knowledge gained thereof to humanity across the continuum of industrial revolutions? While progress in better understanding the universe and how things in the universe work is an important goal in itself, it's also important to translate the impact of science and technology to tangible societal and economic benefits for a larger population, especially if you want to get support for science and technology from the larger population. One of the fundamental measures of societal progress is global average life expectancy at birth. According to various estimates, the global average life expectancy in the world was about 32 years in 1800. 32 years in 1800. By 2012, the global average life expectancy went up to about 70 years. What is impressive is that the population of the world has increased from 1 billion in 1800 to about 7 billion in 2012. Humans are not only living longer, but are also economically better off in general. According to data from studies by the World Bank, the percentage of world's population living in poverty based on purchasing power parity units has decreased from 94% in 1820 to 9.8% in 2015. In absolute numbers, there are less number of people living in poverty in the world in 2015 in absolute numbers than in 1820, despite a 7x growth in world's population. What are the economic benefits of science and technology? Let's visualize the world's GDP in trillions of international dollars on the x-axis of the graph. Let's assume on the y-axis of the graph, let's assume the y-axis goes from 0 at the origin to 127 trillion international dollars, the current world's GDP. Let's denote time on the x-axis. Let the origin of the x-axis denote 8000 BCE, about the time humans started farming, so the agriculture revolution. And let's extend the x-axis to 2018, that is today. The graph of world's GDP versus year, for most part, is a line hugging the x-axis. This reveals the increased step change in the world's economic activity that has been spurred by advances in science and technology from the turn of the 20th century, including advances in information technology. So only at the turn of the 20th century does this graph start to spike vertically upward. That's why this reveals the increased step change in the world's economic activity that has been spurred by advances in science and technology from the turn of the 20th century. In fact, the vertical spike becomes pronounced only after 1950, when computers started being adopted in industry and government. While science and technology lead to societal and economic progress, there are important questions that we may have to answer sooner than later. Some of these questions are becoming more relevant in the context of recent progress in AI and ML. Well, artificial general intelligence, that is human-like intelligence, is still only an aspirational goal. It may be prudent for us to deliberate on what it all means for furthering human knowledge. I.J. Good, chief statistician of Turing's code-breaking team, wrote in 1965, "Let an ultra-intelligent machine be defined as a machine that can surpass all the intelligent activities of any man, however clever. Since the design of machines is one of these intellectual activities, an ultra-intelligent machine would design even better machines. There would then unquestionably be an intelligence explosion, because now the machine is able to create more intelligent machines. And the intelligence of man would be left far behind. Thus, the first ultra-intelligent machine will be the last invention that man need ever make, provided that the machine is docile enough to tell us how to keep it under control." So this was I.J. Good in 1965. So does this mean scientific and technology progress will at some point in time be left in the hands of ultra-intelligent machines? Only time will tell if human knowledge will and can be entrusted to machines. Human knowledge is at an exciting cusp today. In the book Critical Path, futurist and inventor Buckminster Fuller estimated that if we took all the knowledge that mankind has accumulated and transmitted by the year 1 CE as equal to 1 unit of information, it probably took 1500 years until the 16th century for that amount of knowledge to double. The next doubling of knowledge from 2 to 4 units was completed in 250 years by the mid-18th century. By the turn of the 20th century, 150 years later, human knowledge had doubled again to 8 units. The speed at which information doubled was getting faster and faster. The doubling speed is now estimated between 1 and 2 years. So how do humans handle such an exponential growth in knowledge? Ray Kurzweil, an American futurist, predicts that within decades, humans will transcend biology and maybe increasingly getting fused with machines. He believes that there will be a point called the singularity when technological change propelled by the explosive growth in artificial intelligence will accelerate past the point of current human comprehension. While we ponder on the larger philosophical implications, let us look at what has brought us to this cusp. Among the countries that have leveraged science and technology for the benefit of their citizens, USA stands out. USA has taken the center stage in harnessing the latest advances in science and technology from turn of 20th century. While the university, industry, military complex in the US powered science and technology from World War I till the end of Cold War, the university startup complex has been in the forefront of powering science and technology in recent years. The digital computer and internet are applications from the university, industry, military complex era. And web search, social networking, software as a service, the current AI, ML developments that we are seeing are applications of the university startup complex. The central theme of successive US science and technology policy makers from the era of World War I has been to turn to their scientists and technologists in their universities to solve problems of national importance. The university, industry, military complex era traces back to the pioneering efforts of Professor Vannevar Bush of MIT, who took multiple roles in the government to build a strong science and technology ecosystem in the 1940s. One of Professor Bush's students, Professor Frederick Terman of Stanford University, is credited with the startup culture in what is now known as the Silicon Valley. He was instrumental in setting up the Stanford Industrial Park in 1945, which is now the famous Stanford Research Park. It's one of the most mimicked organizations across the world. He encouraged his students, William Hewlett and David Packard, to start HP in 1947, and that started the Silicon Valley. The investments that the USA made in science and technology from the turn of the 20th century generated increased economic activity. New American companies powered by scientific and technological knowledge dominate the list of most valuable companies by market capitalization. The list of companies, however, has seen a churn in the past decades. Again, this churn is driven by the entrepreneurial activity spurred by new science and technological advances. For example, in 1967, the top 5 American companies by market capitalization were IBM, AT&T, Eastman Kodak, General Motors, and Standard Oil. By 2017, this list was very different. It had Apple, Alphabet, that's the parent company of Google, Microsoft, Amazon, and Facebook, all IT or knowledge-driven companies, and all at the forefront of creating new technologies and knowledge, including in the fields like AI and ML. It's interesting to note that none of the companies in 2017 list existed 50 years back in 1967. Facebook, the youngest, was founded in 2004. Today, USA has the most vibrant startup ecosystem that continues the tradition of the university startup complex and that continues to spawn deep technology startups. Deep technology startups are often built on unique, differentiated, hard to reproduce technological and scientific advances. These startups typically have a strong connection to university research labs. Now I'm going to switch to the Indian context. It is heartening to note that India is continuing on the path of nurturing science and technology advancement and using the resultant knowledge for the benefit of its citizens. However, there is more that should be done. I believe that one of the important policy changes that India should adopt is to increase the R&D spend from the current 0.8% of GDP to at least 3%. In comparison, USA spends 2.7%. Private funding has played an important role in the transformation of emerging nations. For example, in the mid-2000s, about 65% of Taiwan's R&D was from private sector funding, up from 30% in the past. India is at a point in history where private funding can supplement government funding in research, and this includes philanthropy. This may be the time to tweak the current rules on corporate social responsibility that mandates 2% of average net profit be spent on specified social activities. What if instead 1% of such funds can be used to fund science and technology results that shape our future? Let us now reflect back on our contemporary history on how we have leveraged science and technology for our development. India too had a visionary like Professor Bush, and that I believe is none other than Professor Homi Bhabha. Apart from being a main architect of building a India's science and technology capabilities in the decades that immediately followed our independence. Professor Homi Bhabha was also instrumental to leverage the knowledge from science and technology to enable India become self-sufficient, self-reliant in strategic sectors. In fact, one can trace back India's IT journey to Professor Homi Bhabha. It was Professor Bhabha's foresight that propelled India to become one of the few countries to design and build a digital computer in 1960, which was formally commissioned in 1962. It's none other than the TIFR, built by Professor R. Narasimhan, Professor P.V.S. Rao, and the team here at TIFR. While IIT Kanpur was the pioneer in computer science education in India in the mid-1960s, TIFR's, I think initially it was called National Center for Software Development and Computing Techniques, NCSDCT, and later I think NCST. Then IIT Madras and IISc soon followed. Now, this is just a PR from my side. For those interested in knowing more about the history and evolution of Indian IT, please download the Itihasa app, and you will find interviews, video interviews from late Professor M.G.K. Menon, Professor P.V.S. Rao, Professor Ramani, Professor Shyam Sundar, who reminisce the role of TIFR in India's IT revolution. The genesis and early growth of the IT industry in India can be traced to the alumni of IITs, IISc, TIFR, like NCST. Two of the largest Indian IT companies, TCS and Infosys, are the result of the knowledge and the human capital created by this Indian educational and research ecosystem. So again, we have created a $170 billion industry, exports of $130 billion. It contributes 8% of Indian GDP, and it's a result of our investment in education, science, research, etc. An important spillover of the success of the Indian IT industry is that it has inspired entrepreneurial activity in India over the past couple of decades. And the first generation of entrepreneurial entities were like Infosys, Wipro, etc. Then the second wave was Mindtree, the third wave, the Flipkarts of the world, the e-commerce companies, etc. And I think this will continue over the next several years. The Indian venture capitalists are also realizing the importance of deep technology startups and are setting up dedicated funds that focus on areas like AI, ML, virtual reality, augmented reality, drones, robotics, blockchain, biotech, etc. In fact, India is building an active angel investor and early stage VC ecosystem. And it's estimated that the angel investment in India was about $250 million. And this is now growing to around $500 million. So I think we are in interesting times. I believe that we need to do more, and that's why I said that we need to increase our spending on research and development. To conclude, I believe that as Indians, we should continue to foster knowledge generated by research and application of science technology. We should also sustain and grow institutions that nurture science and technology, that are the fountainheads of scientific and technological knowledge. It is in these vibrant institutions that our scientists and technologists, especially our young scientists, make discoveries and inventions that can better every Indian's life. We should link these institutions to the startup ecosystem and should increase the funding for research. But last but not the least, we should fund promising deep tech startups. J.D. Tata's prescient words ring loud and clear. In the presidential address at the first General Assembly of the Indian Institute of Science, Bangalore, J.D. Tata said, "No institute of science and technology can guarantee discoveries or inventions, and we cannot plan or command a work of genius at will. But do we give sufficient thought to the nurture of the young investigator, to providing the right atmosphere and conditions of work, and full opportunity for development. It is these that foster invention and discovery. And let me add, this will actually spur economic growth of the country. Thank you very much.